So in 11.6, we're going to talk about segment relationships in our circles, and it's dealing with the chords that occur. If I take a look at this first theorem, it's called the chord product theorem, and basically it's saying that if I have two chords, I've got chord AB and I've got chord CD, and they intersect inside of my circle at E, I would then know that the product of the two segments of one chord, and that make up the one chord, so AE times EB would equal the same exact thing as CE times ED. So basically, if I've got a chord, two chords, and they intersect in the circle, the products of the smaller segments are going to be equal to each other. Best way to go about it is to show you an example. So in my example here, I've got chord GH and I've got chord FE, and they intersect at J. Since I know my chord product theorem, I know that all I have to do is take 14, that's the one segment, times x, because they're all on the same chord. So I take part times part, so 14 times x, and I'm going to set it equal to 10 times 7, or 7 times 10. It doesn't matter which way you go in that, because of the fact that multiplication is commutative. So if I multiply this out, I'll get 14x equals 70, meaning that x would have to equal 5. So chord product theorem says you take part times part equals this part times that part. Alright, so using our chord product theorem, we have an example with archaeologists, and they've discovered a fragment of an ancient disk. And what we're going to do is we're going to calculate the original diameter of this disk from P to R. And what they did, they ended up drawing a chord AB, and they made it so that it was a perpendicular bisector of PQ. And that's huge that they're telling us it was a perpendicular bisector of PQ, because what that then sets up is something from our previous chapter where we know that this segment and this segment are going to be congruent. So if AQ is 5, we automatically know that QB was also 5 inches. Using that information, we can now figure out what the disk diameter was. So I'm going to figure out what the length from Q to R is, and then add that to PQ to get the whole diameter of PR. So using that chord product theorem, we know that if I take 5 times 5, it's going to equal 3 times whatever the distance for QR is. And we'll label that with an X for now. So I'm going to do 5 times 5 equals 3 times x. So 25 will equal 3x. If you divide both sides, we'll end up getting 8 1/3, or 8.33 repeating. So once I've got that, I know, since this chunk is 8 1/3, to find the measurement of PR, all you'd have to do is take 8 1/3 and add on the 3 inches to that to get a total of 11 1/3 inches. So my diameter, PQ, or PR, excuse me, is 11 1/3 inches. So in addition to chords, we like to work with secants. And remember, secants are those line segments that go through my circle. So in this case, I know that I've got secant AE and I've got secant CE. The secant product theorem states the following, that if these two secants end up intersecting in a point outside of my circle, then I know that if I take the length of the entire secant AE and I multiply it by the part of the secant that sits out of the side of the circle, that would equal then the entire length for CE times the part that sits outside of the circle DE. So AE, so I usually say whole times the outside part would equal the whole secant times the outside part here. That's the secant product theorem. So we're going to use that theorem to help us out with this example down below. So I want to find out what the value of x would be. To find the value of x in this case, since we're dealing with secants that intersect at a point outside, we know we should take the whole times the outside part and set it equal to the whole of the other secant times its outside part. So the whole. Anytime you need to find the whole, you're going to add these two parts together. So my whole in this case is going to be x plus 8. Then we have to multiply by the outside part of that secant, which is 8. That'll equal the whole, 9 and 7 add up to give me 16, times the outside part, which is 7. So all you do is do the multiplication. So we're going to distribute my 8 through, and I get 8x plus 64 equals 112. We're going to subtract the 64 and divide by the 8, and we're going to end up getting x is 6. The last theorem for this set of notes is the secant-tangent product theorem. And in this case, it's saying, what happens if I'm not dealing with two secants? What happens if I'm not dealing with two chords? But rather, I'm dealing with one secant and a tangent. So the secant is the one that goes through the circle, whereas the tangent is the one that is outside of the circle and touches the circle at one point. In this case, what you do to solve is you're going to take the whole entire secant length, like you did before, and you're going to multiply it by the outside part, BC. So AC times BC, just like what you did before with two secants. But with the tangent, since there's only this outside part, you're going to set AC times BC, excuse me, equal to DC times itself. So that's why we have the DC squared. Best way to go about it, I'll give you an example here. Notice I've got a secant and then I've got my tangent. So the rule says you're going to take the whole entire secant. So the whole entire secant is 15 plus 5. You do the addition, which is 20, times the outside portion of my secant, which is 5. Set that equal to then the tangent portion squared. So we're going to set it equal to x squared. So I'll have 100 equals x squared, and when you square root both sides, x will equal 10. So you've got three new theorems: the chord-chord product theorem, the secant-secant product theorem, and the secant-tangent product theorem. It's basically just going through and making sure that you know each of those and the process that goes along with it. If you have any questions as to how we set these problems up, please make sure you write them down and you ask your teacher in class. Until tomorrow, have a great night.